Good evening, bachcho. So I hope all are very well and attending classes and studying nicely, right? YouTube wale. Okay. So today we have to study a lot. Okay. बहुत सारा पढ़ना है and study a lot. Okay. Okay. We are live as well. So we have to study a lot. We have to cover our portion and we have to complete the chapter today so that next weekend or next in the next upcoming class that is on Sunday. Before that, you can have one test, right? So let's start without wasting much time. Okay, so in previous class, bachcho, we have completed. Good evening, JNV Mahe. Okay. So in previous class, bachcho, we have completed till this question. Okay, we have seen AC generator also. Today we are going to learn some new things. Okay. First is motional EMF. Let's start with motional EMF already. Acha, for today only, just little bit write fast in the notebooks. Okay, whatever you want to note, because I may not be giving more time to write. Okay, so little bit write fast today. So motional EMF, bachcho, it is an EMF which is produced whenever the conductor cuts the magnetic lines or magnetic field lines. Okay, we have studied that some what do we say, flux. What is flux? Flux is the magnetic field lines existing in an area or crossing an area, right? Whenever we increase the area of that particular body, more lines will cross, flux will increase, right? If we change the magnetic field intensity, if we increase the magnetic field also, the flux will change, because flux is equal to BA, and then theta was there, right? BA cos theta. So if we change the orientation also, the flux will change. But here also, when this conductor is crossing this magnetic field, this conductor is crossing this magnetic field, in some time t, let's say it will come here. Okay, so it has already covered this much area, means it has already faced this much change in flux or this much change in the magnetic field. So in this area, basically, for example, this was a time is equal to 0, it was here. After some time, let's say time is equal to 2 seconds, this rod came here because it is moving with some velocity, let's say v. So it has actually covered this much area, and in this much area, it has felt a lot of change in magnetic field. Okay, so in this case also, there will be flux change and something will happen in the rod. Okay, let's see what that something is. So you have, bachcho, already studied in the previous chapter that whenever a charge is moving in a magnetic field, it will have or it will feel some magnetic force. Okay, and what is that magnetic force? QV cross B. You remember? Let's say if I put a charge inside this magnetic field, it will do a circle and come out, because it will experience a centripetal magnetic force. Right? Similarly, this rod, bachcho, this rod is made up of electrons and protons, correct? Atoms it is made up of. Electrons are free. So if I consider electrons in this rod, and this rod is moving with velocity v in magnetic field, let's say B, where this electrons will feel the force. Can you tell me the direction? Up or down? Upside, these electrons will feel the force, or downside, they will feel the force, magnetic force. I'm repeating the question again. These electrons which are residing inside this conductor will feel a force because they are moving with velocity v in a magnetic field. So what will be the direction of force on them? Reply in the chat. Up or down? Which rule you use? Right hand palm rule, something is there, right? Tell me, quick. Do you remember palm rule? To find the force on any charge moving with the velocity v in a magnetic field, or you can do just v cross b also, correct? Because the force on electron will be qv cross b. Okay, so how we use palm rule? This thumb we point in the direction of velocity, four fingers we point in the direction of magnetic field. The palm will give us the direction of force on positive charge. Okay, so if I put my thumb in the direction of velocity, somewhat like this, and four fingers in the direction like this, so my palm will be showing upside the force, right? So it means that all the positive ions will move up, all the negative ions will move down. Movement of only electrons is possible, so all the electrons bacha will come down. Okay, all the electrons will accumulate. I am telling you the reason why it is happening. All the electrons will accumulate here, so this will become negatively charged and this will become positively charged, means it will form a battery somewhat like this. Okay, JNV Mahe, upward will be the force on positive charge. This right hand palm rule gives the force on positive charge. Okay, negative charge it will be ulta, so that's why all electrons will come down, all positive charge will be coming up, negative charge will be coming down. It will form a battery like this. So whenever, let's say, if I move this pen also, if it is a conductor, if I move it in a magnetic field which is perpendicular to this conductor, then it will become a battery, a small battery. Okay, that's why it is called motional EMF. EMF generated by motion of a conductor in a magnetic field. Okay, chalo. So let's see how we find the magnitude of this motional EMF. So we know that flux is equal to magnetic field into area, correct? B dot A, B vector dot A vector, or we can say BA cos theta, right? So if I say that how much area will it sweep, this flux basically will give us finally EMF also, because EMF is equal to change in flux over some time t. So let's say at time t the rod was here, at time t plus small time dt the rod came here. So how much change of flux happened? This much area into magnetic field. Okay, so this much area is how much? First of all we will write magnetic field into area is velocity into length. Clear? How much area it will sweep? Velocity into length. So the final formula for EMF will be BVL, where B is magnetic field, V is velocity, L is the length. Okay. Acha, now let's say the rod, if it is moving with some angle theta, so our condition is that it should move perpendicularly only, right? So we will make it perpendicular. We will use VBL and component of this length. Component of this length. That will be L sine theta, because this is 90 minus theta, right? So we'll make the rod perpendicular and we'll get the EMF, right? So this is important formula. Please note it. Questions are asked from this area. Okay. Let's move further. Have you noted this? BVL. This is the main formula in scalar and vector form. And how you will determine the direction of positive charge? Right hand palm rule. Point your thumb in the direction of velocity, four fingers in the direction of magnetic field, and the palm will give you the direction of positive. Okay. Chalo. So this is a question for you. Look here. You don't have to do, I'll tell you. So it is saying that find the value of EMF induced in the rod for the following cases. The figures are self-explanatory. So here is a rod in all the three cases, and this rod is moving with the velocity of v, and magnetic field is capital B, right? Now here you can see that B and V are in the same direction. Will it cut the magnetic field? It should cut perpendicularly. Like for example, this is magnetic field. Sorry, let's say this is magnetic field. Okay. Rod should cut it like this. If it is like this, it is not cutting, right? If it is like this, not cutting. It should be like this. It should cut like this. Okay. Because then only we'll get the vector product B cross V. Here you can see now V cross B, right? So then only you will get V cross B. Okay. So here, since B and V are in the same direction, EMF we know is B cross V dot L. So B cross V we can write BV sine theta into L. Sine theta, how much is theta, bacho? Theta is 0. So EMF will also become 0. Simple. Next one. So velocity is upside, right? And the magnetic field is inside. Okay. So here also the magnetic field lines are not cutting. This rod is moving parallelly. Or we can say, what is the formula of EMF? BVL sine theta. Okay. B is there, V is there, sine theta. Theta is bacho, the angle between V and B, that is 90. But length, if I talk, how much is the length of this rod? Length in the sense that in which direction it is moving. Okay. So if rod is moving like this, length is L. If it is moving like this is the length. It is almost 0. So here length is almost 0. That means 0 EMF. Similarly, here also you can find, right? Velocity is in this direction. B is upwards. Okay. Again, the magnetic field lines will not be cutting perpendicularly, right? So here also you will get 0. Simple. Chalo. So this is clear. Aage chalte hain. Let's move forward. Chalo. So there is a question. Let's do this question. Okay. Read it once quickly. 30 seconds to read. Chalo. Look here, all of you. It is telling there is a rod PQ of mass M and resistance R. So this rod is having a resistance of R, and it is free to move over the rails. Okay. Resistance-less, smooth conducting rails. So these both are smooth conducting rails on which this rod can move freely. Okay. Closed on both the sides by resistances R1 and R2. Find the current in the rod at the instant its velocity is V. Okay. So it is asking what, bacho? It is asking the current in the rod. Okay. So when this rod will move, actually here magnetic field is also given, which is inside. So when this rod will move, where will be the direction of it? Will this rod will become battery, correct? This rod will become battery. By using right and palm rule, we can find the direction of battery's positive terminal, right? So if I point the thumb in the direction of velocity, B in the direction of this 4 fingers, so I'll get the force upwards on positive charge. So upwards is the battery, means positive is upwards, negative is downwards. Clear? And what will be the EMF of this battery? EMF is equal to BVL sine theta. Theta is 90, sine 90 is 1. Okay. So the EMF is BVL. Now we can redraw this circuit, bacho. If I redraw this circuit, positive battery, R1, R2, small r, and positive battery, which is having BVL as the EMF. Okay. Now how to find the current? you can see, if I redraw again this diagram, because see here, this point is A, this point is B. This resistance is connected over AB, and this is also connected over AB. So these both are in parallel. Okay. So I'll just remodify and tell you what is the simplest diagram. This is R1, this is R2. This is R and this is BVL. Now it is easy to find current. Current is equal to voltage by resistance equivalent. So voltage is BVL by equivalent resistance. These both are in parallel. So it will be R1, R2 upon R1 plus R2 plus these two, and this internal resistance is in series. So plus a small r. This is R equivalent. So R equivalent is R1, R2 upon R1 plus R2 plus a small r. So this is the current. But your note, quickly note. Late joiners. Join on time, bhai. Very important topics. Chalo. So let's move forward. Short mein likha karo questions. Questions you write in short. Just make the diagram and write everything in the diagram. This is R1, this is R2. We have to find current. So put I is equal to question mark. It will save time, right? In writing. Chalo. So let's move forward. Now let's see induced EMF due to rotation, because when the conductor is moving or cutting the magnetic field lines, it can cut in circular motion also, in rotational motion also, correct? So here also the same thing is happening. It is cutting when this rod is moving in circular motion in this magnetic field B, it will be cutting the magnetic field line. So some small EMF will be induced, right? So how to find that EMF? It is important. The result is important. I am feeling like to give you the derivation also. So I'm doing derivation also. Listen very carefully. Okay. So let's say in a small section dr at a distance r, a small battery formed. Okay. The direction of battery will be palm rule use karo. The velocity is downwards. Let's say it is moving with angular omega. Okay. So velocity is downwards. Velocity is here, which is omega r, omega L, sorry. Right. So velocity is down, magnetic field is inside. So this palm will give me the direction of positive side. So this will be the positive side. I'll just make it. This will be the positive side. Okay. By using palm rule. Now it will rotate and it will cut the magnetic field lines. So how it will cut the magnetic field lines? So flux is equal to BA, correct? Magnetic field is B. Area that it sweeps in, let's say, dt time. Area that it sweeps in, let's say, dt time is the length of that small section, length of this small section, dr, into velocity, this much area it will sweep, right? Okay, into in how much time it swept, dt time. Clear? So this is area swept and dt is the time. Now if I replace this velocity by omega L, because v is equal to omega L, so I can write not omega L, it will be omega R. Okay, because this dr element is at a distance of r, not L. And a small mistake here, it is R. So we will write here B dr dot omega R dot dt. So this is the flux in dt time. This is the flux for a small section dr. So for this whole section, we have to integrate, because whole section will have different flux cuttings, right? So when we integrate, or when we find EMF, EMF is d phi by dt. Okay. Acha, this is change in flux. Sorry, this is change in flux. So we'll put the value here. D phi is B dot dr dot omega r dot dt divided by dt. dt se dt cancelled out. So from here, EMF is equal to, we have to integrate this, right? So R is from 0 to L. And if I integrate this, I'm writing the final result, which is B omega L square by 2. If you don't understand the derivation, the final result you can remember. Only this result will come. Please note it. B omega L square by 2. Or half B omega L square. It sounds like half MB square, right? Half epsilon naught E square. So many formulas are there. Quick. Please note it quick. Lack of time. Because I have to complete it anyhow, hai na? I think you also want to complete it anyhow. Chalo. So let's move forward. Okay. Self-induction. This is a very important topic. Question comes, right? So first of all, let's understand the concept of self-induction. It is a story. Listen, all of you. Self-induction. What is the meaning of self-induction? So let's say this is a coil, conducting coil. Listen carefully. Huh? It is a story. It needs connection. So this is a coil and there is a magnetic field which is changing inside this coil. And let's say due to this change in magnetic field, EMF will be induced in this coil, correct? And let's say current is flowing because it is a complete circuit. So EMF induced, current is flowing, let's say I. Clear? What I told, there is a magnetic field which is changing. Due to this changing magnetic field, EMF is induced by Faraday's law of induction, and then current is running in this circuit. Okay. So now let's say if I increase this current, pay attention, bachcho, if I increase this current, what will happen to the magnetic field? Not this magnetic field. The magnetic field which will be formed due to this current. Because see, if I forget this magnetic field, in this coil, if current is increasing, some magnetic field will be there, correct? Some magnetic field will be induced, we can say. By using this thumb rule, we find the magnetic field, correct? So current is, curl the fingers in the direction of current, you will get the magnetic field. So when this current will increase, magnetic field also increases, which is induced magnetic field. Correct? Now, this induced magnetic field, if it increases, due to this magnetic field, the flux increases. Due to this magnetic field, the induced flux increases. And when this induced flux increases, means this flux which is induced wala, not from the flux which is this wala. It is from the induced magnetic field flux. If this increases, there is another reverse battery is formed. Because what Lenz told? Lenz told that whenever you will do some change in the circuit will oppose it. So when you increase the current, when you increase this induced current inside the circuit, it will get an opposition. This battery, which is induced battery, is formed. And this induced battery will give another small current, let's say I dash, and will try to reduce its own induced current. This battery, which is induced battery, this will give a current which will try to reduce its own current, which is called self-induction. Self ka induced current will try to reduce the current, its own current. That is called self-induction. Okay, I'm repeating again. So there is a magnetic field which is changing. This changing magnetic field will induce a current in the circuit. This induced current, if I increase, then due to this induced current, there will be a magnetic field induced, which will also increase. And when this magnetic field will change, it will induce or it will give a change in flux, which is induced flux. Due to this flux, a reverse battery is formed by Lenz law. and this battery will try to reduce to this induced current. Means if you try to increase the current, it will feel some obstruction to increase. That obstruction is called induction. Okay. Chalo. So I can say that the flux, which is directly proportional to the current. Flux is directly proportional to the current in this coil. To remove this proportionality, a constant is added, which is called coefficient of self-induction. Okay. This is called coefficient of self-induction. Fine. Coefficient of self-induction. Okay. The SI units is Weber. The SI unit is, in the next slide I will tell you. Chalo, anyhow, Weber per ampere, or in short it is called Henry. Okay. In short it is called Henry, which is denoted by capital H. Clear? Note karte jao. Note it fast. Okay. So what is self-induction? Ye note kar liya ho, then I can move in the next slide. Quick. So what is this L? L is coefficient of self-induction. और आगे जाके हम इसको इंडक्टेंस भी कहेंगे, राइट? ठीक है, चलो. So let's see 2 points on the self-induction. Self-induction is the phenomena of the induction. Sorry, if the inductor, not induction, of the inductor. नहीं, induction ही है. Phenomena of induction of EMF in the coil due to its own current. Okay. It is the phenomena of the induction of EMF in the coil due to its own current. And coil opposes the change in current in it due to its own induced current. So whenever you will try to change the current in a coil, it will not change easily. It will feel some obstruction due to that induced EMF, which is due to self-induction. Okay. Chalo. Now, bachcho, if I take so many coils like this, if I take so many coils, it is called a solenoid, right? That will also we will see. So this is the conclusion basically, that phi is equal to Li. Important formula you have to remember. And L is coefficient of self-induction. SI unit is Weber per ampere, Henry. And this only depends on the geometry of coil. It does not depend on current and all, right? That's why it is a constant. It is constant for every coil. Chalo. So let's do a question quickly. A question karte hain, right? You will not do. Read the question. Look here. So it is telling find the coefficient of self-induction of a small circular coil of radius r. Okay. So there is a small circular coil. Radius is capital R. We have to find the coefficient of self-induction, means we have to find L. Clear? Acha. So for finding L, bachcho, we have to get answer in terms of R and something, right? Of course, we have to get answer in terms of R. Okay. So how we will do it? Look all of you. If you go back in your history, not in history books, in the history of physics, not in the year's history, in the previous chapter. So in previous chapter, you have studied magnetic field due to a coil which is carrying a current I. It was, if you remember, try to remember what it was. Try to remember. Magnetic field due to a coil at the center if it is carrying a current I and radius is R. It is mu naught I upon 2R. Got it? Chalo. So if I say that what is the flux? Flux, bachcho, is equal to BA, magnetic field into area. What is magnetic field? Magnetic field is mu naught I upon 2r, and area of this coil is pi r square. So 1r say cancelled. So it will be mu naught pi r upon 2 into I. Okay, this is equal to 5. Now, just now we have studied that the relation of self-inductance, that is phi is equal to Li. Correct? Just now we have studied in the previous slide. So if I compare from here, this basically is the self-inductance L. So what is the self-inductance of this small circular coil? Acha, why it is told small? Because let us assume that the magnetic field is same everywhere inside the coil. This magnetic field, bachcho, is of the center, right? Center per, what is the magnetic field? Mu naught I upon 2r, not at any random point. Correct? But we are assuming very small circular coil, which is also given in the question. So let us assume that magnetic field is same everywhere. That's why it is small coil. Okay. So what is self-inductance here? Mu naught pi r upon 2. Okay. Chalo. So let's move to solenoid. So if I increasingly put the coils together, it will form a solenoid. Okay. And it is also called an inductor, right? So we have to find self-inductance of this solenoid, right? So how to find the self-inductance? Do you remember the magnetic field due to this solenoid? Again, the story goes on. First, we will find magnetic field. Then we will say phi is equal to BA. We will put the magnetic field there. We will put the area there. And then we will get the self-inductance. We'll compare with phi is equal to Li, right? So what is the magnetic field, if you remember? B is equal to mu naught Ni, small ni. And what is small n? Small n is capital N upon small n. Okay, so this is the magnetic field. Now, if I want phi, that is equal to BA. This is for one coil. If I take n number of coils, so it will be NBA. Correct? It will be NBA, right? So if I put the values here, n into magnetic field B is mu naught Ni into area of this coil is, let's say radius is small r. Radius is small r. So it is pi small r square. In place of n, bachcho, we can write NL. So I can say phi is equal to n square mu naught pi r square n square mu naught. Just a second, did I miss something? No, it is correct. N square mu naught pi r square. In place of n, bachcho, we are writing NL. That's it. Into L into I. Okay. Now comparing with phi is equal to Li. So this whole quantity is self-inductance of solenoid. Okay, which is n square mu naught pi r square L. Clear? So sometimes in questions it is asked, okay, the self-inductance of solenoid is directly proportional to length, is directly proportional to radius, is directly proportional to number of turns per unit length. Something it will ask like that. Okay, so this is basically the formula, and self-inductance from here of solenoid is n square mu naught pi r square L. Clear? Chalo. Noted? Acha. So when coil is kept in a magnetic field, some EMF is induced, right? So each coil will have its own EMF. If I sum up all the EMFs, this coil will behave like a battery. A single coil behaves like a battery. So if I sum up so many coils and form a solenoid, those whole coils will form a total EMF, right? So let's see that. So potential difference across an inductor. So let's say it formed a battery. It formed a battery somewhat like this, right? And what will be the EMF of this battery? So there is a derivation which is not required for you people. Just remember this EMF, that is E is equal to L di upon dt, where L is same, self-inductance of the coil. Okay, I hope you have seen this formula somewhere. Please note it, very important. Let's do a question then. Oh, 20 minutes only. We have to cover a lot of portions still. LR circuit I have to explain, right? Chalo. लिख लिया phi is equal to di by dt. Now there is a question. Find induced VA minus VB, means we have to find the battery potential basically. If the current increases by 3 ampere per second. So just now we have studied EMF is equal to EMF of this solenoid is L di by dt. Okay. Inductance is given already in the question, which is 2 Henry. Change in current is 3 ampere per second. So 6 volt is the EMF across this inductor. Okay. Chalo. So let's move forward towards LR circuit. Very important. 99.9% question comes. That's why. Okay. So in this coming 20 minutes, you should fully concentrate on LR circuits. We have studied what is inductor, and also I'm directly putting it with resistance. Okay. Listen carefully here, all of you. So there is a battery, a resistance, a inductor of inductance L, self-inductance L. Short form I'll call L. So when I close this switch, current will start to flow. Current will start to flow. And if I apply KVL here in this circuit, so how I will write? E minus IR minus this will be basically a battery forming, right? It will be forming a battery which will be of L di by dt. Just now I explained, right? L di by dt. So minus L di by dt, which is equal to 0. Okay. So this is equation, or we can write it in this form also. E is equal to IR plus L di by dt. So what I'm trying to do is I'm trying to find the relation of current, how the current will happen in this coil. Okay. Chalo. Of course, if inductor was not there, current will directly reach to E upon R. But inductor is there, means some problem will be there. Okay, let's see that problem. So I close this at t is equal to 0. Okay. Now I'll do it in next page. Yeah, here only I will do. So if I little bit change it, if I bring this here, so it will be like E minus IR is equal to L di by dt. Okay, please pay attention on the derivation. Now if I take L downside, and if I take L downside and take dt here and take this whole quantity down, so it will be like 1 upon L integration, or I can write integration out of integration, dt is equal to integration di upon E minus IR. So what I'm basically doing is I brought dt terms on one side and I terms on one side. Okay. Now listen carefully. At t equal to 0, when I will just close the switch, at t equals to 0, when I will just close the switch, the current will be 0. Why, sir? Because I told you na, this inductor will behave like a battery whenever current passes through it. Just initially I'm talking. Later on it will not behave like a battery, but initially it will behave like a ulta battery. It will oppose the change because of its self-inductance. It will oppose the change of that current because of its self-inductance. So at t is equal to 0, current will be 0. So I'll put the lower limits as 0 for time and current 0. After some time, let's say the time t, after some time t, the current reached, let's say I. Okay. Now little bit of calculation I'll do. Please see that calculation quickly what I'm doing. So 1 upon L integration of dt is t, limit is from 0 to t, is equal to integration of E minus IR is ln E minus IR, and again limit is from 0 to I, and IR ka integration is minus R, so that is in denominator. Now if I bring this R on this side, so it will be minus 1 upon or R upon L. This will be T is equal to ln okay, from here 0 to I will put the limit, so it will be ln minus or ln E minus IR. Okay, so here also the limit is from 0 to I, so that I have put. So here what will be remaining? Minus. Okay, I have just put the limits here. If I put I inside, it will be E minus IR. Then when I will put 0 inside, it will be E minus ka E. So that minus ka E I have put here. Okay, and it will be in terms of ln E. Sorry, it will be in terms of ln E. Okay, chalo. So, acha, one more thing here. There is something called time constant. So L by R is called time constant, which is denoted by tau. This is called tau in seconds, right? So in place of R by L, I can write tau. Okay, so here I will write minus T by tau is equal to ln E minus IR upon E. Okay, ln something minus ln something is ln something upon something. Now again, this derivation continues here. So here ln base E is there. So I can write E to the power minus T by tau is equal to minus R by E into I minus, sorry, plus 1. Because E by E gets cancelled out. That minus will come this side and it will become like this. Okay. So if I resolve it, I'm writing directly. So I will get as E by R. If I take E by R common, 1 minus E to the power minus T by tau. So this formula you have directly seen in your books, I think. So this is the basic derivation. Okay. Derivation is not required, but just for knowledge, I told you. So basically what is happening? The current in the inductor is decaying with exponential rate. Sorry, increasing with exponential rate. Initially the current is 0. At t equals to 0, the current was 0. Now it is increasing exponentially with this. So this is a very important formula that you have to remember. Chalo. Okay. Chalo, let's move forward. Only little bit time is left. So if I talk about this formula, at t equals to 0, current is 0. If current is 0, means it is behaving like an open circuit. So very important, at t is equal to 0 means when the switch is just closed, inductor behaves like an open circuit. Open circuit means the wires are open. They are not connected. So current is 0. And at t equals to infinite means after a very long time, put here t is equal to infinite in this place. So it will be e to the power minus t, or sorry, e to the power minus infinite, and e to the power minus infinite is 0. So it will behave like current will be I is equal to E by R, and it will behave like closed circuit or short circuit, we can write, not closed circuit, short circuit. Short circuit means the inductor is itself not there. Okay, you just see this circuit. If inductor ko gayab kar do, then what is the current? E by R. So after a very long time, there is no significance of inductor. Acha, these we are talking for DC battery. For AC battery, the story will be different. Okay, so this is very important. Please remember this. Okay, and the graph, if I talk at t equals to 0, I is 0. So the graph will start from here. And at t equals to infinite, it is E by R. So this is E by R, maximum value. So graph will go somewhat like this, which is exponential graph of current and time. Okay. Chalo. So quickly, let me tell you one more. Let's do one more question. One question quickly. Okay. Chalo. So in this question, all of you pay attention. In this question, it is telling that you have to find initial currents in all elements and final currents in all elements. Okay. So if I talk about this circuit, initial current means when the switch is just closed. When the switch is just closed, at t equals to 0, inductor behaves like a open circuit. Means current in inductor is 0. So this inductor bachcho is not there at t equals to 0. If it is open circuit, that means only the remaining circuit is this much. So what is the current? It is at t equals to 0, current is equal to E by R equivalent. So E is 14, R equivalent is 12 plus 6 because it will be parallel because there is no circuit here. So it will be 18. Okay, solving is your part. Now if I come across final current, finally at t equals to infinite, the inductor behaves like a short circuit. Means current is max, means it is E by R. Sorry, here I have done mistake. I have found it for infinite. Initially the current is 0. So finally the current is E by R. So at t equals to infinite, because little bit in hurry I am to complete since 2-3 topics are there. Listen all of you. So I is equal to E by R and it will be 14 by 12 plus 6. Okay. Chalo. Now if I want to find the time constant, sometime time constant also it asks. So time constant, the formula is L by R. But sir, the problem is how we will put the value of R. Which R we should put? This R or this R or this R? So for that, what you have to do is you have to put R equivalent. For tau equivalent, you have to put R equivalent. R equivalent across what? Across inductor. So for that, what you have to do, bacho? You have to open the inductor, and short circuit battery. So how the circuit will look like if you open the inductor and short circuit the battery? Somewhat like this. Okay, so this is 12, 6, 3. This is open. Now find the resistance equivalent across this AB or this inductor. So how much it will be? This is 12, this is 6, both are in parallel, 12 and 6. So it will be 12 into 6 upon 12 plus 6. That is 4. And 4 and 3 are in series. So total is 7. So tau is equal to L, that is 16 upon 7. Clear? Chalo. So for finding time constant, you have to just find the R equivalent across the inductor. So for that, what you have to do, you have to open the inductor, short circuit the battery. Okay, when you will come in graduation level, when you will do BTech from electrical engineering and all, you will learn there are some theorems, Thevenin theorem, Norton theorems. So in those theorems also, the short circuiting is done of the batteries and current sources. Anyways, let's come to decay of current in LR circuit. Okay, so I will not derive it. I'll just give the formula. What is the meaning of decay of current? For example, in this circuit, if I first close this switch K1, if I close, so this battery will flow the current and this L will become a battery. Okay, so it will become like a, after time, infinite means after a long time it will behave like a small battery. Okay, now if I talk, this battery will have some EMF, that is LDI by dt. Correct? LDI by dt. Now if you disconnect K1, and if you connect K2 now this battery will discharge. This inductor will discharge. And when this inductor will discharge, the current will flow. And that current is also decaying with exponential formula, which is I is equal to I naught e to the power minus t by tau. Okay, please note it. This is current decaying formula, where I naught is maximum current, that is E by R. Okay. Chalo. Let's quickly move to another topic. Just write the formula. Derivation is not required for this. Okay. So now let's come to one or two important formulas. One is magnetic energy density. Okay. So it is the energy stored per unit volume in magnetic field. In electrostatics, you have been studied electrical energy density. If you are not studied, I'm telling you. So if there is an electric field in some area, if you take a volume, in that volume also electric field will be there. And what is the meaning of electric field? It is an energy. So how much energy is stored in that volume is called the energy of electric field, and that energy divided by that volume is called energy density. Simple. Okay, so that energy density, electrical energy density if you remember, the formula was half epsilon naught E square, where epsilon naught has its usual value 1/4 pi epsilon naught, if you remember, and then E is electric field, the magnitude of electric field. Similarly, here also in magnetic field, if I take a volume and if I find the energy density, that is energy by volume, here it is written energy by volume, it is B square by 2 mu naught. Okay, the SI unit is joule per meter cube. Please note it, only this formula. Energy density is equal to B square by 2 mu naught. And it is density. Remember, it is energy by volume, not the total energy. Question will come, find the total energy in this volume. So you have to find energy density and multiply by volume. Okay. Chalo. Next. So how much energy is stored in the inductor? Because inductor forms a battery, just like capacitors, bacho, if you remember. Sorry. If you remember, just like in capacitors, positive plate, negative plate, positive, 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 negative, negative, negative. There is an electric field inside this capacitor. Okay. And energy stored in this capacitor is half CV square. Kuch yaad hai? So this inductor is also an energy storage device. It stores energy in the form of magnetic field. Capacitor stores the energy in form of electrical field. So how much energy is stored in the inductor? Half Li square, where L is the self-inductance, I is the current. Please note it. Another formula. कर लिया भाई. Chalo. So next topic is mutual inductance, है ना? So after this, only this question is there, which I'll give you as homework. Don't worry. Last topic of the day. Let's complete it quickly and complete the chapter. So mutual inductance. What is the meaning of mutual inductance? First of all, mutual inductance is the inductance created mutually. For example, I am here and there is a girl far away from me, right? So little bit when I see her, I may be induced. Okay. So in that way, between these coils also happens. So let's say there are two coils. One coil is having current I1. Another coil will get induced due to this coil. How? This current, when it will have some current I1, it will have some magnetic field. Correct? And that magnetic field, if I say the direction of magnetic field, it will be somewhat like this. Okay. And this magnetic field, what is the magnitude of this magnetic field, bachcho? Jo bhi ho, whatever it is, let's say B1 is the magnitude. Now, when this B1 will interact with this second coil, it will induce a current in this coil. Okay. It will form a EMF in this coil and it will induce a current in this coil. Let's say that is I2. Okay, this induced current is induced by mutual induction. So how to find mutual induction? Look here. This is coil 2. This is coil 1. So if I say flux linked with coil 2 due to 1, that will be directly proportional to self inductance, or let's say that will be directly proportional to the current in the first coil. Okay. Flux linked with second coil due to first coil will be directly proportional to current from the first coil. And if I remove this proportionality constant, mutual inductance will come. I1. So this is called mutual inductance. Okay. If I think ulta, if let's say I2 current is flowing in second coil and first coil gets induced, so that also we can write, if phi1 induces flux linkage with 2, then also Mi2. Okay. And also this mutual inductance depends on geometry. Depends on geometry. Okay. Chalo, so it depends on geometry, medium, and relative orientation, means how the coils are oriented with each other. Okay. So this is a question for you. Okay. Since time is not there, we will discuss it in next class. And try this question once. If you want answer, I can type your answer also. Try to match your answer. Mu naught N1 N2 A upon L. Okay, this will be the answer. So that's it for this class, bachcho. So it was so much of informative class. Now your work is to practice. Okay. Okay, if you have any doubt, you can ask me. Otherwise, you can. That's it for this class. Good evening, Surana. I have not seen your message. Awai, any doubt? No doubt. So finally, we achieved our target, completed electromagnetic induction. Now your work is to practice. You can use any books which you want, right? Okay, JNV Mahi. Welcome all of you and bye-bye. Let's meet in the next class on Saturday. Have an awesome week.